A covalent bond is a shared pair of electrons between atoms, usually non-metal atoms, but not exclusively. I want to start by looking at ammonia, NH3. Once again, with covalent bonding at A level, we only need to show the outer shell electrons. Nitrogen has got 5 electrons in its outer shell, so it can use 3 of them to form covalent bonds, single covalent bonds with hydrogen, and then it's going to have a pair of electrons left over, which we can represent up the top there. If I have a look at water, we have a similar thing going on here. Oxygen, it's got 6 electrons in its outer shell. It can use 2 of them to form a covalent bond with hydrogen atoms, shared pairs of electrons, and then it is going to have 4 electrons left over, 2 pairs of unused electrons. And these pairs of unused electrons are known as lone pairs. So oxygen has 2 lone pairs of electrons commonly when it bonds with anything, could be hydrogen or not hydrogen. And also ammonia, therefore, has 1 lone pair of electrons. And these lone pairs of electrons are particularly useful when these molecules are reacting, and they can be also used to form dative covalent or coordinate bonds to other atoms, molecules or ions. Ammonia has the ability to react with hydrogen ions to form an ammonium ion. Let's have a look at the bonding in this. So we know about ammonia, let's start there. Got a lone pair of electrons and then 3 single bonds to 3 hydrogen atoms. Ammonia can use this lone pair of electrons to form a bond with the hydrogen, and the hydrogen is able to accept this pair of electrons because the hydrogen ion has no electrons of its own. And then the positive charge that belongs to the hydrogen ion is essentially taken on by the whole molecule. If we remember about hydrogen, hydrogen has 1 electron, so 1 electron and a single proton, and if it loses that electron, then all we have is the proton. We have space to accept a pair of electrons from the nitrogen. We can show that more simply perhaps as simple lines to indicate the shared pairs of electrons between nitrogen and hydrogen, and then an arrow is used to show that the bond to the 4th hydrogen is actually a dative covalent bond. The electrons are being donated by the nitrogen to the hydrogen. Another common example where we have a dative covalent bond is the molecule carbon monoxide. You might be aware that there is a triple bond between the carbon and the oxygen. Carbon has got 4 bonding electrons. It uses 2 of them to form normal shared covalent bonds with the oxygen, and then it keeps a pair of electrons back as a lone pair. Oxygen does the same, but oxygen has got 6 electrons in its outer shell, so it uses 1 of its lone pairs of electrons to form a dative covalent bond to the carbon. So we can indicate that as 2 lines to show normal covalent bonds where 1 electrons come from carbon, 1's from oxygen, and then the arrow to show that oxygen's donated a pair of electrons that the carbon has accepted. We can also have dative covalent bonds between molecules. An example would be between molecules of aluminium chloride. Now, despite aluminium being a metal, it's got 3 electrons in its outer shell, 1, 2, 3. It forms covalent bonds with chlorine. Chlorine has 7 electrons in its outer shell. And as you can see, that in this molecule of aluminium chloride, aluminium does not obey the octet rule, which is something you might met at GCSE. We commonly said at GCSE that once atoms are bonded, they have 8 electrons in their outer shell. This is not the case with aluminium, it has 6, which allows it to form dative covalent bonds with a second aluminium chloride molecule. So how might that work? Let's have a look. So if I were to draw a second aluminium chloride, I'm going to draw it in this position here. These are the 7 electrons around each of the chlorines. Let's get them all nicely drawn in. You can see, I hope, that in this arrangement we could have a chlorine making a dative covalent bond to one aluminium and vice versa. And when that happens, essentially what we've made is a molecule of Al2Cl6, and it's a dimer. So we've got two molecules coming together, bonding using dative covalent bonds to hold them together. It might be clearer if I were to draw it with lines instead. So we could have our first molecule, we could have our second molecule of aluminium chloride, and then the dative covalent bond between one chlorine and one aluminium in each case. In some molecules, the atoms have more than 8 electrons in the outer shell. This is known as expanding the octet, and this is common for elements in period 3 or above. Let us take sulfur as an example. Sulfur's got 16 electrons, 1s2, 2s2, 2p6, 3s2, 3p4. But we know that the third shell has another set of suborbitals. It has the d orbitals, and in sulfur they are empty, but they are there, which means that more electrons can be accommodated. This gives sulfur and many elements in period 3, the non-metals, a much bigger range of possibilities when they bond. So sulfur can form 2 single bonds, as in SCl2. In this case, sulfur behaves just like oxygen, also in group 6, and it forms 2 single bonds, each with a chlorine atom, and it has 2 lone pairs of electrons. 2, 4, 6, 8, 8 electrons in the outer shell. However, in SF4, sulfur retains 1 lone pair of electrons, but then forms 4 single bonds with fluorine atoms, and we can see here that sulfur has 10 electrons in its outer shell. Finally, we might think about SF6, in which case sulfur uses each of its 6 electrons, the S2 and the P4 electrons, to form 6 bonds, each with a fluorine, and we will have 12 electrons in the outer shell of sulfur. The octet has been expanded. And finally, a word on ions. I'm thinking, for example, of ions like hydroxide, OH-. Between the oxygen and the hydrogen, we have a shared pair of electrons. Oxygen has 2 lone pairs of electrons, and it has 6 electrons altogether in its outer shell, which means that it's got space to accept an electron from elsewhere. And if it brings on an extra electron, it will now become negatively charged. This electron, for example, might come from, if it were reacting with sodium, the sodium. The metal cation is formed by the loss of an outer shell electron, and that electron can be picked up and shown in my dot cross by the use of a third symbol to show that this electron didn't originally bond to either the oxygen or the hydrogen, it is from elsewhere. If this has been useful, hit the subscribe button, the effortless way to support your studies, and by clicking the link in the description below, it'll take you straight to Crunch Chemistry School, where you can access my free maths skills course, complete tuition, and worksheets designed specifically to build your confidence and stretch you. Together we can do this.